in this sort of complicated Kobayashi-Maskawa matrix, there are things hidden which are worth going through. But how did it all start? The other day I gave you an argument. I have not been feeling well, so I hope it will go okay. I just barely got up for the class. What I did last time, I gave you a physical argument why there had to be the Chang quark. Right? We had problems understanding the homology of the kaon system. Alexei talked about it before in his course. But let's see it, we can see it even from more formal. I mean, after all, especially there are a number of you who don't care so much about homology, you tell me. So you can also think from the formal point of view. If I say that there is an up and down doublet, and I know that from weak interactions, and then I tell you there is another quark which is exactly like the down quark, and it has the same interactions with the up quark, right? This strange thing about strangeness. Then, of course, by structure. So if I say that there is another quark, there must be a completing state to give me the same structure. This is the beauty, if you wish, of the SU12 cross U1 gate theory. It says, even if you don't know homology, that there had to be a Chang quark. So if you had taken that seriously, you would have said, look, they had to be there. Then you learn that that had to be another generation for the sake of CP violation. We'll review that argument briefly. These are doublets. We were talking about here, it's sort of nice to separate because the physics of two generations. When people come my age, they claim that the world was much better when they were young. They will all tell everything was better. Football was playing better for football hour. Men get together, girls were nicer, younger people are better behaved. None of that is true. Okay? One thing, however, was nicer. There were two generations only. And that's much easier. Think of this, okay, just one mixing angle, okay, instead of that mass that somehow you have to remember today. An advice. People used to laugh at me. Very often when I want to understand something new, we would work on some problems in graph unification, whatnot. I want to do it in two-generation case. It turns out, actually we've written a couple of papers with my collaborators that turned out to be important because you can get a lot of insight when you can see simply analytically what goes on. And I advise you to do that. Look at the complicated case only when you have to. That's the final step. So, then of course there are up and down quarks. And so on. There can be more, right? There can be more generations. Okay, we said before particle hermesis, they are not particles. Right? Before they are physical, well-defined eigenstates of the mass matrix, doesn't make sense to think of them as physical particles. So we had a subscript 0 to emphasize that. Right? In our SU2 cross U1 gauge theory, there was no place for mass term. That would break the symmetry, right? Doublet cannot mix with a singlet. And so it came from a Yukawa interaction, which these are QL I states. We'll talk about lepton separately. And these are URI and DRI states. I is the index that counts the number of generations, right? Everything came from the Yukawa interaction. There was a down quark, Yukawa. And then there were similar terms for the up quark, but remember at the end it boiled down to the, I'll just write down the down quarks for the moment. And we said, because of the symmetry argument, SU2 cross U1, all the states are equivalent. There is no up quark and down quark. You agree? This is just, this notation is actually not so good. This would be better notation to pull them just to 1, 2, 3. The masses at this point, so how can I distinguish them? So we said this will be a matrix in the end with a subscript 0 plus Hermitian conjugate. So down, let's look at down quarks. And we said this will produce, we wrote like this. Sorry, not. It came from the doublet structure, right? By writing phi unitary 0v plus h, we immediately reproduce this. And then unlock her for the upward. So we said we can write this in the following manner: dl0, m down, dr0, 1 plus h over v plus Hermitian conjugate. This is in the massless form, where the states dl are 0 would be d, s, b, and so on, 0, left, right. Okay, this way I can get rid of the index. And then we said we can diagonalize it by writing u, l, m, u, r. We'll take the down quark mass matrix and we diagonalize it by having different unitary rotations on left and right. This is often called dd or MD, which stands for diagonal matrices M down, M straight. This is now physical, right? I'm using a theorem from linear algebra that I can take a general matrix and diagonalize it by left and right. To get a feeling what these are, you can look at the combinations M dagger. Okay, M dagger is Hermitian, you agree? And notice that this is what we get. UL is the matrix that diagonalizes M dagger, and similarly UR diagonalizes M dagger M. Right, by forming this Hermitian conjugate, I get an insight what UL and UR are. Notice that you have two n, the general matrix has n squared complex elements, that's 2n squared real elements. Unitary matrices have n squared elements, if you remember. The counting tells you that you have the right matching to be able then to have this in the real form. I will use the freedom of phases always. You probably remember that the sign of the Fermi mass is not a physical quantity. It's not even a phase, if you remember, if I have one particle. Remember what mass is. Mass is this for us. The sign. We have conventions when we give a plus sign to the mass. Okay, all we have is m squared. But in case of the fermions, when you have FL, FR in general, remember this plus Hermitian conjugate, you could have a phase here. You can rotate one of these fields to eliminate phase. So by convention, we write the masses in the positive. So, as positive numbers.
We call these terms mass, but as you said, in principle they are complex numbers, and we can make it look real using the freedom.
Using the freedom will make it real. That, of course, will fix my UL and UR, and then we'll see how much freedom it remains. We'll have to analyze that freedom in a few minutes. Okay, we have to be very careful. Once we have fixed our conventions, then you will see, because we'll have to count the number of physical phases that appear in these matrices. Okay.
So there are there are no complex masses ever, right?
No, because by convention, there is no meaning here, because the mass of a fermion, you see, put it in this form. Okay, suppose that you didn't believe me, and so there will be a phase alpha D, alpha S, alpha B. Okay. Notice I stop at 3 generations. There is a reason for that. Okay, I'll tell you why we are basically sure that there are only 3 generations. So I would get a term with a phase. Notice I can now rotate fr, and nothing will change. And I have a unitary matrix here that I didn't say that is a SU matrix. It's just a unitary matrix. Okay, U dagger are defined as 1, both left and right. They are not SU matrices, okay? This phase freedom is very important, okay? This, in other words, I will write as dl bar md dr 1 plus h over v. Once I go through the process of diagonalization, I of course pick up physical states. These are now physical states. Okay, dl right is really down strange bottom quark. There is no zero index left right in such a way. And remember, MD is this DD. These are matrices, okay? You will have to see from the context. I will use the one and the same notation as everybody else. That's for the down quarks and for the down quark. Very good. Plus Hermitian conjugate. But this is nothing but d bar d md d bar d 1 plus h over v. If I had kept the index, I would write sum over I could write like this to make sure that you understand. The index is hidden here. I can. Okay, this is clear, I hope. But as if I have only one generation, right? The beauty of the Higgs interaction is that there are no mixings whatsoever. Any questions here? This is the basis for everything else that follows. Our mixings, the physics of charm and strange particles and the decays all comes from this necessity to diagonalize quark mass matrices. And the way I wrote it, dl r0 would be u left right. This was the definition, d left right. Maybe I would, maybe I should put a vector here or something to distinguish it. Okay, but too many indexes. I hope I don't lose you here. And as I said, the meanings are clear. Okay. What we have to understand then, where will these mixings u left and u right go? And you knew from Alexei's-Cost that they go into the W physics, right? The only knowledge is there, and why? So this is the Higgs vector. The Higgs interaction is universal as a structure, and is proportional to your mass if the Higgs couples to you. There are no mixings here. Why? In a sense, you knew that because masses and Yukawa couplings are one and the same thing. Higgs accompanies the web. Web gives me the mass. When I diagonalize this term, I will diagonalize this term. Okay. It's even more clear here. You diagonalize the mass matrix, you diagonalize the Higgs coupling. Agree? It's funny that the mixes come from there, but there they disappear. From there they go somewhere else where they were not. They will go here. So really what I could write here, this will be true for any fermion species that have the mass. Because the Higgs interactions with universal, we check it on leptons, on charged leptons, on up quarks. Okay, neutrinos is something else, we have to talk about it as we go on. But this is actually true of all the massive fermion states. So I have first the W boson, the weak interaction, charged. Which I could write as G over square root of 2 U CT 0 L D S B 0 L W mu plus. I put it immediately in the vector form. All I have to read, up couples to down, by definition they are in the same doublet. That was just a notation anyway, there should be I and J. Charm, too strange. Top to bottom. This would be the picture if there were no mixings. This would be the story if the masses were there to start with. But these were massless particles, okay, this interaction. We often call this as a weak basis. This is the basis of weak interactions. You can keep writing in this basis. Then you have to work with complicated mass matrices. Okay, in the end the physics will end up being the same. Where you put your mixing is up to you. What we do, we want to have physical particles, it's easier than to read off things. And this is then by definition G over square root of 2 U CT and so on L gamma mu UL up dagger UL down DSB L W mu plus. This is called VCKMA. The Higgs interactions, strangely, which were all ugly and complex, became real and simple, but the gauge interactions, the W interactions, became ugly and complex. If there are many generations, this is a terrible thing to work with. The fewer generation, the easier. One generation, of course, there is nothing to talk about, but then there is no interesting dynamics, there are no strange particles, there are no decays, okay. 3 generation becomes a little messy, but still manageable, okay. So I, for one, would be very happy, and I'm getting there, knowing that there are no 4 generations, okay, that would drive me crazy. Let's do some counting and try to understand it. So what I know about VCKM, by the way, we speak about mixings in the W interactions, but not in the Z interaction or photon. Why? Remember, I introduced you in the charm core because I had a problem with the mixing in the Z. That's gratifying. We didn't want to have mixings in the Z boson interaction. If you have mixing sets, you get a disaster. Remember, we got K long, K short, orders of magnitude too big.
Because you have Z dagger, you have these one.
Precisely, because the Z boson takes same species. For any species, you can write as FL, and whatever. F will stay for up quarks, for down quarks, and this goes into Z. Sorry, it starts like 0. As Macbeth says, it will go into FL, UL, F dagger, whatever species. and this is 1. So the neutral gauge Boson's photon is the same. And that's gratifying, because this is the way the world looks like. So the structure of the standard model, this may be simple, naive. The minimal structure gave us what we like: a massless photon, reproduce correctly interactions, and on top reproduce the Z boson interactions. No mixing here. Okay, let's understand the mixings here. So when I have a unitary matrix, because of it has two, a matrix n times n will have two n square elements, but there are n square conditions. So V actually has n square elements, real elements. When V is real, then we speak of orthogonal matrices. How many elements does the orthogonal matrix have?
N squared.
Almost. Or 2. And then minus 1. Remember, you form it with antisymmetric generators, okay? They had to be antisymmetric, they were imaginary, okay? So, these n square elements we call n minus 1 over 2. Do you agree that I can write like this? This is trivial. These are, however, called angles by convention, because this would remain if everything was real. So these are called the generalized Euler angles. Right? In the case of 3 rotations, we will call them Euler angles, okay? And these are called phase, right? This is the complex part, okay? Let's do the counting. This was the question that Mehmet was asking, so let's go back to that. What are really these phases? How physical are they? When I write this matrix, okay, it seems that I have a lot of phases. Even with one generation, I will have how many? One phase. But let's look here. Once again, manifestly. Just to see what happens with one generation. I will have UL, DL, W plus. Let me not write indexes. We will have G and then E to the I alpha. The counting tells. But now I say, you choose. Who should we take? Let's take a downward. I can have DL E to the I alpha called DL prime. Of course, I must at the same time rotate the right-handed quark to make sure that the mass remains. Remember, should I erase them? These are our masses are put in the real form so that we can talk of them as a reaction to the gravitational field. Say, okay, a positive number. Conventions that you and I use for us. And I have to preserve that. Therefore, whenever I rotate left, I rotate right. Equally. Then, of course, the mass will stay real, right? The Fermion mass term can be written as Fr. So I must write both left and right if I want to preserve the phase convention, okay? But the right-handed quarks have no weak interactions. This is an interesting structure of the standard model. So I can keep rotating right-handed quarks, nobody will know. And I will do that. So therefore this phase is not physical. In other words, I get rid of this and this becomes, I will call this a down quark. In other words, Well, now you can do it for 2 generations, okay, and you would conclude, I don't want to do it like that the phases will disappear also. But instead of doing it sort of in a studentish manner, let's do the counting, which I believe you could done with it, may not. So I'm just saying that, so let me calculate the number of physical you see, in order to have CT violation, remember you had to have something complex, okay? I can remind you of that. But just remember that for the time being, or take my word for that. Of course, that's necessary but not sufficient. I must have such a phase that I cannot get rid of it by the phase redefinition, okay? So this is a tricky part, and it's very easy to be wrong here. To imagine a situation where the phase is physical, but it's not. So number of physical phases is, in other words, it's not n plus 1 over 2. But I can redefine the phases of the quarks. And nothing will happen if I do this little exercise, right? How many quarks do I have? N generation is 2n. So I should have minus 2n. What would I get, for example, for 3 generations? 0. But those guys got the Nobel Prize, okay, correlational scala, so it's got to be a phase. Where am I wrong? Not only you have to be careful to see what is physical, you have to be careful to see what is not physical, okay? In other words, I'm saying, so let's do it now. Okay, let's do one studentish thing. So let's say, I'm going to make a phase definition. UL will go into the I alpha, let me call it up, UL. And the same for right. Okay? But I'm now looking at the phases in the left-handed sector. And then charm goes into the I alpha charm CL. Top goes into E to the I alpha top TL, and so on. And DL. Let me write like this. Let me do something stupid. I will write E to the alpha U UL. This I will write E to the I alpha U. E to the I alpha C minus alpha U CL. This I will write E to the I alpha U, E to the I alpha T minus alpha U TL. I know it's stupid, but let's see where it takes us, okay? So down quarks, DL goes into E to the I alpha D DL, which I will write as E to the I alpha U, E to the I alpha D minus alpha U DL, and so on. Again, I take E to the alpha U here, and so on, right? I don't have to keep writing. Why did I do this stupid thing that I've taken out? Note, this is an overall phase, and I have the same overall phase here on up and down quark. But the weak interaction takes me from up and down quark, so this disappears. There is no such phase. I was wrong. I was almost right. I can redefine almost 2n phases, but one I can't. There is always one which is overall, and the overall we cancel between. And I don't have to write this in such a manner. I should just think. One of these phases I can pick up to be the same. It's a convention, and it will disappear. Now, what do I get for 2 generations? What do I get? 0. But for 3, I don't get 0. let's see what it is. Who is quick? This is nn plus 2 minus 4n plus 2 divided by 2. This is n squared minus 3n plus 2 divided by 2. This is n minus 1, n minus 2 divided by 2. This is the number of physical phases. And this little mathematical exercise has a fantastic, profound, deep meaning, right? This is what Kobayashi and Maskawa, this little exercise, they had to do this little exercise. They realized, well, everybody knew at the time, that people were wondering how to solve the problem, that there was no CP violation, okay? It took courage also at the same time to say that there will be new particles. And they said, okay, for 2 I get 0. For 1 I get 0, I could see that explicitly. For 2 I would just do the game. And for 3 I get 1 phase. So although there are 3 mixing angles and the matrix is messy, at least there is 1 phase, and that helps a lot, because that means that all the CP violating processes will be relating. The K on physics, the B physics, whatever, will have 1 and the same phase. That already tells you that the model is very constrained. And that's one of these little miracles that we love about the standard model. All the CP violation works beautifully. But let's have a look at this. Someone has a computer on you so that I don't open mine? No. To dictate the CKM matrix, but I have mine here if you wish. I'm going to write it on the blackboard. I want us to. You can do that.
Yeah.
Okay.
CKM.
Right, but or even it's here. There are various forms. I want the. It's here. You can just. Let's see if I can try. I'll try to reproduce it. Let me see. I'll fake. But I pause a little bit just to see if you guys want to ask something.
Physical means measurable always, right?
Physical means measurable, means something that you cannot, or well, means measurable of course, but that means that you cannot get rid of it by redefining the masses, okay? And you will see how we, you see in the 2 times 2 case, when you write the, just to remind you how it goes. What happens is if you write the unitary matrix in 2 times 2 case, then it has C e to the I alpha, S e to the I beta, something like this. C e to the minus I alpha. There is 1 oral phase. You can easily see that this you can eliminate. And notice that these phases they are kind of external. You are sandwiching with this between U and C and D and S. So they are picking up the phases here. You can't hide them. But you see what Kobayashi and Maskawa notice. When you have 3 generations, okay, this is just accounting, which is useful to know that there better not be 4 generations. God, 3 phases and 6 mixing angles. I would hate particle physics if there were 4 generations.
But looking for 4th kind of neutrino is not
No, you know there are no 4 neutrinos. That you know from your homework. Even if there are other generations, the so-called neutrinos would have to be very heavy. You computed the number of neutrinos in the Z-boson physics. I'll have to summarize the W and Z physics and the Higgs physics. When we are sort of leaving the standard model towards the end, we'll do that once again. Look at those salient features. And that's somehow there are 3 light neutrinos. That doesn't mean that there are 3 generations, as for example was written in New York Times at that time when when this was established, because the fourth generation neutrino could be very heavy.
That's also possibilities of fourth quark generation by variables.
Yeah, well, that we'll have to talk about it. LSC is getting rid of this possibility, okay? We'll have to talk. Let me not simplify. So, what is it that they do? Like, well, they say I will write the CK matrix. I'm going to write as a rotation, orthogonal rotation 2, 3. So now n is 3. Then I will write V13 with a face here. And I will write O12. I'm told that there is one phase, I didn't count it. But you see, I'm going to put it somewhere in the middle so that it will not be acting, there will not be an external phase because I can get rid of external phases, okay? I have to do more, I can't just put it on the outside. And here is the trick. So what does it mean when I write this U? What would this be? Let's write here. You understand the notation? O23, for example, is what? 1, C23, S23, just the usual 2 times 2. I call it orthogonal. No phases here. And this V13 would be C13, 0, 1, S13 e to the I minus delta. The popular, the most commonly used version of Kobayashi-Maskawa is not the Kobayashi-Maskawa, is Jung-Chal. Version. And when the dust settles, okay, this is sort of, let's write it here. So it's going to have C 1, 2, C13, I guess. You wanna? You tell me. So because of that, this will be, and then this will be
S12.
S12. You see?
S12. C13.
C13. So this must be. Now, don't tell me this is obvious. You and I, let's get. You know this is unitary, so it has to add to 1. When I square this, this gives me C13 squared, therefore this must be S13. And there could be a phase. It turns out that there is a phase, and I think it's minus delta with the convention I took.
Yes.
Am I right?
Yes, yes.
Here I'm going to have C13, no, C12, C23. And here I'll have C23, C13, among other things. So what am I going to, well, I should have written like this, C12, C13, and then there is a product of all 3 angles, I believe.
Yes.
Okay. So minus S12.
Minus
And then there is a phase, but I don't remember, plus or minus?
Plus.
Plus. E to the I delta.
But it's the second one is C23. It says C1, C12, C2.
2, 3, yeah. Correct. This is. So if this is C23, C13, what should this be? And this is S13, so this must be S23, C13. Something like this. Is there a phase? No.
No, no.
What else? Can we try to figure it out together, just to see how far we could push it? It's going to be ugly. These two are ugly, okay, that I remember. So if I have C12, C13, I should have S12 here. These should reduce. I need to get Kabiba rotation. Remember, if there are only two generations, if S13 is 0, if S13 is 0, I should go back to Kabibo. This will be S12, this will be S12. So this will be C13. But then there will be plus or minus some combination, I don't know.
But it says C23.
Here, there is also C23.
No, only it's not one. Maybe there's C1, but C12, C13, but
oh, it's C23. Well, this would be 1 also, okay? You see, you can't really guess it.
yeah.
So this must be S12, S23. Right? Because I have to sum this to 1. And then there will be ugly terms. Okay, here I stop.
They are minus both. No, the first one is not.
Minus, and here plus?
No.
And now you have to tell
both
me.
minus, and this is minus also.
This is minus? Okay, well, of course. That I know. Okay, you see, we can... I have to sit down, I'm not feeling... I wonder whether with some thought we could figure out, okay, but maybe it's not so illuminated. Okay, because this is messy, so therefore this can be also messy. I mean, when we square this to 1, it's a mess. So what do you get?
C12,
C12,
S23,
S23,
S13.
S13, and then there will be a phase.
The phase plus.
Okay, they should be at the same level, okay. And here, therefore, there will be minus?
Yes, 1.
Something similar, right?
Yes, basically the same, except the midterm is C, not S. So C12, C23, S13.
Phase.
With the positive.
And then well, maybe we could have guessed it. Suppose that 1, 2 is 0. Or maybe we wouldn't have guessed. Okay. Anyway, one can just multiply. But I think with some thought, maybe we could guess it. And here, therefore, I will have there will be S23, right?
Yes.
With C12.
With a minus and 4. Yes.
Minus or plus?
Also minus.
Minus. And then Someone has a guess? I could look at the limit. Suppose that S23 is 0. If S23 is 0 and S12 is 0, then I should have the matrix which is just, oh no, but then it will be 0. S13 0. I need S23, but I have S23. No, I have. I'm just not feeling well enough. Tell me. Help me.
S12.
S?
S12. C23 and
It completes this guy, okay. This. So it should be S13.
S13 with a positive phase.
Why do I bug you with this? Okay, you're still with me. I know it's we're just writing a matrix, okay, bloody hell, what's the use of writing a matrix? I want us to get some insight. For example, notice that if I take theta 1, 3 to 0, there is no phase. You agree? And that was a convention. We put the phase with S13. Now, physics cannot be depending on my conventions, what I call 1, 3 or 1, 2. That means if I set theta 2, 3 equal to 0, I should conclude that there is no phase. You agree? Because otherwise the physics would depend on what I call 1, 3, and that's sort of crazy. So if, physical reasoning, I expect, so I put a question mark, no phase. But it seems that there is a phase. Let's put S230. What will happen if I put S230? This will disappear. This will disappear. This will disappear. This will be 0. And there is a phase. So what's going on?
Also in the one of the corner, first one.
Important. This is what you see. I'm bugging you with it. Seems just a silly exercise of staring with arguing 3 times 3 matrix. We can learn a lot physically because this boils down to your question: when is the phase physical? Okay. Now I'm deducing it cannot be physical, but it's there. Of course, the fact that the phase is there doesn't mean that it's there. You can write 2 times 2 with phases, but then you compute whatever you compute. Those phases are going to cancel because there are no physical phases. Like say did accounting already in October or November. But you see, I can still keep rephasing my quarks. For example, I can get rid of the phase here and put it here. I can multiply by because this is 0. I can multiply correspondingly. I leave you this exercise, please. Maybe I include it when I show this. I'll indicate how. I take this phase out. Okay? By proper redefinition. Or if you wish, I multiply by e to the I delta here. That is redefined the phase of I don't know, down one of the down quarks, I guess. That means it will disappear here, but it will appear here. Do you agree?
Also up.
Sorry?
Also in the first two. In the first couple. It'll appear also.
Do I want that? No. Bless you. Who says that there should be? Emilio said, right? Well, this is, what is this term? It comes from U bar, this is U bar D, right? This is U bar S. And this is U bar B. And this is C bar B. And this is T bar B. So I have just redefined the phase of the B quark. I'm not going to touch those.
Okay.
I'm glad that you asked me. See, you've shaken me a little bit. Now notice what is nice, okay? It disappeared. It's only here. And it's one row which has the same phase. That I can do easily. That's just, so what is this? This is T bar D, T bar S, T bar B. Oh, I'll just change the phase of the T quark and nothing will go wrong. And so on. The answer here is there is no question mark. Similarly, take theta 1, 2 equal to 0 and play with it and you will see that there is no phase. And this is very important. Because there is a sort of nice question that you can ask, where CP violation is so weak. Why is CP violation so much weaker than, after all, the phase can be large? And the reason is that the same reason that explains the K long, K short physics, okay, the hierarchy of the mixing angles, okay, it turns out that the mixing angles are small. You have to say a few words about it. Theta 1, 2 is about 13 degrees. And theta 2, 3 is about 10 to the minus 2. And theta 1, 3 is 10 to the minus 3. You have a next neighbor approximation, okay? You like to couple to your neighbor. Okay, you don't like to, sort of. So the language of generations is often called families. There is something of a family. Family likes to stay together. And then it couples a little bit to other families. So you have a social network. With a strong emphasis family life. Okay, a very traditional picture, okay? These are practically zero, these mixing angles. And we'll see that it's important that they're zero. I'll remind you why. That's how it all fits. We'll come to that. But what I've just shown you, the CP violation, that parameter dimension that it measures, must be proportional to theta 1, 2, theta 2, 3, and theta 1, 3, because whenever one in each of them goes to 0, the phase disappears, times delta, or sine delta, whatever. I'm being very cavalier here. There are signs of the angles, okay. Mehmet.
That's what I was going to say, because where I put my complex phase matters in the end matrix.
It's just a convention. The result cannot depend where you put it.
It should not, but...
and it does not. I can show you.
I mean, if I choose to put my delta in O12, then I will have a different matrix.
Well, but the result will again, you will get the same result, physical result. It will be the product, the CP violation will have to be the product of all three mixing angles. What you call, the name will change, okay, so your phase will not be maybe my phase when we talk to each other. What you call the top quark, you and I have to have same convention in order that the communication goes on, whatever we talk about. But that's just language, that's not physics. Physics is the independence of that thing, and it's hidden here. If anything, if the CP violation looks a bit too small, remember it's supposed to be 10 to the minus 3. That's because there are enhancement factors. For example, the mass of the top quark and so on. I'll have to say a few words. But I don't have to assume that CP violation is small. I don't have to put a small phase. CP violation standard model came out, was predicted to be small. Universal and small. From the fact that the mixing angles are small, we'll see why they are small as we go along. I have to now discuss with you how will I see those mixings. They appear they're very important, they appear in the neutral sector, they play a major role there in K long, K short. But I made the Z boson phase angle independent. There is no mixing. So, well, we'll talk in a minute after you. This is why I wanted to write this matrix, just sort of for you to see the pattern and why this smart manner of hiding it in the middle guarantees that you are not going to be able to eliminate it. Start playing, forget the counting, start playing, say, oh, I will redefine this core. You see, because it's here, and it's not just an overall phase. You'll never manage to get rid of it. You'll get rid of it here, then it will come here, and so on. It's a genuine physical phase. And actually it turns out to be pretty large. It's not small. It's about 40 degrees or something. What is small are these mixing angles. And this is why I keep reminding you, CP relation you can forget about. The standard model practically conserves CP. Except for the tiny. It breaks charge and parity maximally. Parity and charge conjugation takes you left to right. That's broken. CP then by definition takes left to left. By the way, let's get there. One quick reminder. So I'd like you to convince yourself, which I sort of outline here. That should be more or less clear. But one thing, I'm saying that the CP and the parity, remember what we said, psi goes into gamma 0 psi. That was equivalent UL going into UR. And the charge conjugation, psi goes into I, this was our convention, gamma 2, gamma 0, psi bar transpose, which is I gamma 2 psi star. So this is under parity. And this is UL goes into I sigma 2 UR star under charge conjugation. So under CP, UL goes into I sigma 2 UL star. This is why CP can be a symmetry of the standard model, because left goes into left. And the standard model is all about left-handed particles. So here we are looking at the double interaction. The other interactions, remember, they don't even know anything about the mixings or anything. They're all one generation, okay, Z. And here is the... and just to see how much you are familiar with notation, we would look at the interaction, let's say, UL bar. Well, UL, this is psi 1L bar, gamma mu, psi 2L, W mu plus. Now U is not an up quark, UL and UR. Okay? This would be one of my species, one up quark, one down quark. There is a coupling here overall, but... okay, what would this... how can I write this? This I can write as U1L, U1R, dagger, gamma 0, gamma mu, U2L, U2R, W mu plus. Sorry, this is 0. I project it. I'm just looking at the left-handed component. What is gamma 0, gamma mu? Gamma 0 is 1. Gamma 0, gamma I is 0, 1, 1, 0, 0, sigma I minus sigma I 0, which is, well, we have to erase this. Minus sigma I, sigma I. In other words, this thing here, we often write like this, as sigma mu bar, sigma mu. Are you familiar with this notation? Sigma mu is identically 1 Pauli and sigma mu bar is 1 minus power. You have familiarity with this? It's good to know both the two-component and four-component notation. Sometimes two-component is more useful. For example, in this particular case, it's quite useful. In other words, this interaction becomes U1L dagger sigma mu bar U2L W mu plus. And I can see very quickly what happens under CP. Imagine that this had one coefficient which I called A. In general, remember there is a phase, because the thing here is that there is Kobayashi-Maskala matrix, and therefore A is G times some mixing angle, right? U1 stands for one of the up quarks, one of the down quarks. What does it go into under CP?
I conjugate.
So it would go as A. No, A is a number. A cannot go into. A number goes into a number. Fields change under. This was my coupling, okay? A is G over square root of 2 times U1, 2 element, or no, V C K M element, which I don't know. IJ, 1, 2 is not good, okay, well, of course, I don't mean 1, 2 matrix element. Doesn't matter, whatever it is. It goes into E, U1L, you see, I can read from there. It goes into I sigma 2, U1L star dagger, sigma mu bar. U2L goes into I sigma 2 UL star, and then this is W mu plus prime. Can you remind me how the gate boson transforms? Remember the photon? Let's start with the photon and the parity. How does the photon transform on the parity? A0 goes into A0, and this is a vector, right? This is a scalar, this is a vector. What about charge conjugation? Minus sign. So under CP, A0 goes into minus A0, and AI goes into AI. What would you expect as a generalization? This is for the photon. What about W? Well, W plus 0 will go into W0 minus. Particle has to go into antiparticle, okay? We use the same definition under parity, but under the charge conjugation, it's not a question of minus sign, it is W plus becoming W minus. The rest, of course, they're the same Lorentz structure field under parity, so Wi plus goes into minus W, no, plus Wi minus. This is under CP. And therefore, let me just outline, this would be A, the same coefficient. Can you see what's going to happen? Sigma 2, well, let's just write down. There will be U1L transpose, I sigma 2, sigma mu bar, or maybe minus I sigma 2, sigma mu bar, I sigma 2, U2L star, W mu plus prime. This is W mu plus prime. Okay, these are the transformation properties. Okay. So now you have to figure this out. I leave you as a little exercise. Maybe I do it. Just to be at least finish the outline. Minus I and I gives me 1. What is sigma 2, sigma mu bar, sigma 2? What do you think?
Minus sigma conjugate.
There's going to be A, U1L transpose. Sigma 2, I'm asking, sigma 2, sigma mu bar, sigma 2. Right, but I don't want the complex conjugate. I don't want the complex conjugate. This will be the proportional, okay, maybe to sigma mu complex conjugate, but there is a better thing that I need. You see what I want to do? I want to move to here. So this is proportional to sigma mu transpose, I'm guessing. Is it true? Emilio, I can see, is awake fully. Okay, I see all of you guys have been with. Look, sigma 0. Sigma 2, sigma 0, this is 1, will give me with a plus sign sigma 0 transpose, they are the same. What about with sigma 2? Sigma 2 commutes with sigma 2. So it leaves sigma 2. But sigma 2 transpose is minus.
It gives like a sigma complex conjugate, just complex conjugate. Sigma minus plus. Without the bar. Bar is just changing the sign, right? Yeah, that's why.
I feel like putting a minus sign, but sigma 0 is bugging me.
Bar is just makes plus or minus sigma matrices. Bar is not.
Sigma mu bar is minus.
And for sigma 2, we just got sigma 2 complex conjugated, and others are the same. So
Right, but I don't want to speak of complex conjugate. Why should I speak of complex conjugate?
It's just yeah, because they are Hermitian.
Because they are Hermitian, we can complex conjugate it again.
Okay.
That they are the
So
same.
no, you are saying there is a minus sign or plus sign here?
Plus without bar. No, with the bar. Okay.
Yeah, with a bar.
No, without the bar. Because sigma 2 goes minus sigma 2 conjugate.
No, maybe you are right, okay? I should have written, by the way, let's write it here. The original interaction was A, psi 1L bar, gamma mu, psi 2L, W mu plus, you agree, plus, this was the original interaction, we started with this, plus A star, this is where I put A star, I have a Hermitian conjugate, this is psi 2L bar, gamma mu, psi 1L, W mu minus. This is what I know. What is this? This is A, U1L, sigma mu bar, right? U2L, we said. W mu plus A star. This is U2L dagger. Sigma mu bar is the same sigma mu bar, U1L, W mu minus. No, it's okay. I know what I was doing wrong. This will be, there is no way, this is neither plus or minus. It goes like this, it is plus, so it is A, U1L transpose. Then I have to separate the zero from the others. They don't have the same property. This is very important. Neither do the gauge fields. So what you get here with a plus sign, sigma 0 bar U2L transpose. And I have W, what is W plus 0 prime? Is minus W0 minus. Okay? Plus a U1L transpose. Okay, now I did it. You will get a minus sign here, minus sigma I bar transpose. Trivial exercise. So this is plus when it's 0 and minus for I. You understand? Sigma mu bar transpose. I cannot write one in the same manner. So okay, I can do a little better. This is sigma 0 bar transpose minus sigma I transpose. I don't want complex conjugate, I want the transpose, it's convenient. I have a minus sign here, but I have a plus sign here. So this is Wi plus Wi minus, which I can write as A U1L transpose sigma mu transpose bar U2L star W minus mu with a minus sign. I have a minus sign here and I have a minus sign here. You're following me. I know it's the end of the day. But here we are. What did I get? I got A. Now I will commute these two guys. And that has an extra minus sign, so I get U2L dagger sigma mu bar U1L W mu minus. So what I showed for you.
In the last step, we took this extra conjugation, or
Where?
in the last step.
Here.
Uh-huh.
Here.
Uh-huh.
This is just this written in the.
And then
Then I'm interchanging this. Then transpose, of course, you go into the psi 1 some matrix, so psi 2 is minus psi 2 transpose O transpose psi 1.
we use this for
Obvious, because there are ij, so O becomes O transpose. Do you see that, please? You would have here index I, how do you call alpha, Lorentz index, beta, O alpha beta. This would be beta, this would be alpha, this would be alpha beta, but this is O transpose beta alpha. I use that, of course. So what I showed for you, I wasn't going to do that, but now that I've done it, this goes into A psi 2L bar gamma mu psi 1L W mu minus. The first term I took. Or if you wish, I show it here. The first term went into A U2L dagger sigma mu U1L W mu minus. So in order to get CP violation, A must be different from A star. The Lagrangian I had here A star, but I just show under CP violation, this remains like this. So CP violation is equivalent A differ from A star. You must have a complex coefficient somewhere in order to get CP violation, and that must be a physical term. It's something that you cannot eliminate. Okay, but you and I know with 3 generations we are okay. I should have let you do that. But anyway.
Just a question.
Yes.
In the last part, yeah, in the last part, we could have argued also that we had a real number. All the expression was real, so we can take the transpose of it.
What do you mean that it was real?
I mean, the whole
Nothing was real. It was
no, the whole expression. All the expression, not term by term.
No.
All the expression was.
No, this was the term. There was nothing real here. The Lagrangian, that's why I had the Hermitian conjugate. No, this is manifestly complex.
If you do the same tricks with both terms.
No, I will do this separately. Forget this. This was just written in order for you to see what is going on. This is what I've shown. This is what I've shown. Okay, I'm glad you are asking. The Lagrangian has this plus this, but this goes into this instead of going into this. And this, of course, you can do this separately, will go into A star, the other term. So if A is different from A star, there will not be CP conservation. The Lagrangian will not go into itself. The interaction will go into the complex conjugate of the interaction that is supposed to go. And vice versa. If the couplings are real, of course, that you are sure. Okay, maybe it's good that I've done this.
I think what he wants to do.
But this is not, it's not enough that you see this, me doing it, okay? I don't see you doing it. If you have not done it here, you have to go and do it at home. The way to do it, just do it, says Mike. Not by seeing someone else do it. It will evaporate. So I don't know whether that will be on some homework, okay? There is not enough time to do all these homeworks, okay? I've done it a little roughly on purpose. This is something you should be familiar with. You think you got it? Okay.
Because we did something similar in the 3D course, but we argued that the term that we have was part of the Lagrangian, so it was a real number, and we took the transpose of it, arguing that it was a real number. So since we exchanged particle with antiparticle, Fermi with antiparticle, we got a minus sign from there. So it was very similar to this. That's why I was asking about it. But now it's clear, because if we take also.
Okay, so once again, this is what we've shown.
Okay.
This term goes into this term. And in order to be CP equivalent, you should go into this. The Lagrangian went into the sort of complex conjugate of itself instead of going in itself. Okay, the Lagrangian is not invariant. I've done it purposely into two-component notation. I will be using it rarely, but from time to time, you've seen some of my notes, some of the decays. Sorry, I've done in the. So where am I? We now know, you and I, that the CP violation. So if I want to get CP violation, I have to involve the top quark and the bottom quark. It won't happen if I look. For example, I can look at K long, K short. But before I do that, okay, we have to spend a few minutes. We'll finish it next time, just to prepare the territory. How in the world will I get that K long, K short mixing? The other day, what I did, when there was no Chan quark, I got a Z interaction. And the Z interaction was changing twice down quark into strange quark. Or I could have written like this, for example. I could have taken like this, put SD. So S bar D went into S bar D, if you wish. That's how you look at it. How will I do it now? There is no interaction with the Z boson that violates strangeness. I have to go from neutral states. In other words, I have to go from here, the same thing that I did there, D, become S, and for example S becoming D. And I can't exchange the Z boson. If I do that, it cannot happen. Z doesn't do that. I take
Two bosons and
Two-
one other family in between.
two W's. W is shy, so it's not sufficient, so I can do this. This could work, precisely. So I do this, and inside I propagate. So who is this? This is going down. What is this? W minus, and this is W plus. Correct. These are called box diagrams. Good. So you see, I don't want to compute it, but maybe you could. The nice thing about this is that it's finite, you know, you see the things, how divergences cancel, disappear, okay, so it's, but there is, it takes some time. Let's see why this works. When I did this thing, what I found out that this was proportional, I would have gotten G Fermi, sine squared theta cavivo, and then times the interaction. And that was terribly big. Now, without doing any calculation, I'm going to say this itself will be proportional to G Fermi, because this has this interaction has how many dimensions? 4 fermions. 3 halves, 3 halves, 3 halves, 3 halves. That's dimension 6. So it goes as 1 over m squared, therefore it has to be G Fermi. That famous thing, G squared over mw squared. But there is a loop. So if there is a loop, there's be another factor alpha over 4 pi. I'm lazy. Okay. And also, let's forget the top quark. Let's go back. The reason I can forget the top quark, you're saying, but it's crazy, top quark is very heavy, it may dominate that. It mixes very little. Okay, the third generation basically decouples. In the first approximation, I can go back to 1969. The Jim guys. Let's estimate. Let's do what Jim did. Okay, we have still some strengths. Okay. If up propagates, then there is cosine theta here. And remember there are no phases. This is nicely 2 generations. Okay, maybe it's just. And then here there is sine theta cavivo. This is for the up quark. So I'll get twice sine theta cavivo. But that I expected because that would have happened anyway. So there is sine squared theta cavivo. And then there will be this interaction, psi bar psi. Then I estimated. So I'm getting suppression compared to the thing at the tree level, which is usually the loop suppression, which is another 10 to the minus 3. But I was off by 7 orders of magnitude, or 6. So there is more to it. It seems that my naive reasoning, which is saying, I got the right dimension, I got the right mixing, I got the right loop factor, where did I go wrong? I don't want to compute. I'm just, I want to leave it for you. Notice what I was arguing. Imagine that the quark mass is a 0. Then there will be no mixing. What sense would be? What do you mean that you are rotating 0 to get 0 again? Now there is actually more than that. Remember what we did? We said, where did VCKM come from? VCKM, U dagger, ULD, right? You agree? Okay. But what were these matrices? Remember what they say, for every fermion species we said there will be something like this. Now, imagine that the fermion has the following form, that it is unity times some m. In other words, imagine that the particles you are diagonalizing have the same mass. Imagine that the generate situation. Okay? Okay. In that case, notice the unity, any matrix, U dagger, unity, any additional rotation leaves this matrix invariant. In other words, if this diagonalizes my matrix, okay, let me think of my up quark matrix. So I'm taking M up equal to M char. In that case, I will say the following, that the VCKM, I can take now ULU to be the prime, to be ULU times whatever U I want. Any U, you agree? This is equally good as this one, because this does not affect the diagonalization of the mass matrix. But I can change U to be ULU to the minus 1. And I can go into the basis when ULD is equal 1. Remember, the basis I choose. The physics cannot depend on the basis. In other words, what has to happen? If the fermions in the loop are degenerate, there should be no mixing. In other words, this here there must be additional coefficient which is proportional to, it turns out it goes as the square, m charm square minus m up square proportional to mw square. It has to have dimension 1. It has to vanish when these masses are degenerate. It has to vanish because I've just convinced you that there is no mixing angle in that case. Why really what happens? You can think here. Look what you have there. You have, take the upward. Upward continuous sine theta cavivo, cosine theta cavivo, you agree? 1 over k slash minus m up. What about charm quark? There will be minus sine theta cavivo, cosine theta cavivo. Charm quark has the minus extra sign. This is the orthogonality of cavivo rotation. 1 over k slash minus mc. When mu is equal to mc, I get 0. And this you can write as sine theta cavivo, cosine theta cavivo, k slash plus mc over k square minus mc square. And this is minus k slash plus, mu, k square minus mc square. And actually you will convince yourself that this goes through k slash. The chirality projection, only left-handed fermions appear here. And I don't want to do this calculation. The thing that this process goes through k slash. And so you get the square of the masses. And this is what the gym guys noticed, okay? And in a brilliant, quick, intuitive understanding. This is in 1969, they said, what will appear is this. They didn't compute the coefficient, so they didn't want to give a precise number. But you see now, instead of getting G Fermi and sin squared theta cavivo, which the Z boson was giving me and was bugging me, I got 3 orders of magnitude suppression. And I got suppression depending on the mass of the chunk quark. So now you can go, from here you can predict the mass of the chunk quark in order to have enough suppression. You tell me how much suppression you want, and I'll give you the mass of the chunk quark. So you talk to an experimentalist. The precise calculation was done in 1974 by Gaillard, Mary Gaillard, and Ben Lee. And they came with the correct number. In 1974, the Slack and Brookhaven experiments showed the chunk quark. It's very interesting. I remember the same Jim people, Miami, I think, wrote a paper suggesting that this could be a new gauge boson. Even the Jim guys didn't take the Jim paper serious enough to say, oh, you are seeing the Jim. And not only that, at the same time as these guys were seeing the guys, they did the actual computation in which they got precisely the right number that would correspond to the Jim particle. Experimentally, they did it by accident, got Nobel Prize. But Jim didn't get a Nobel Prize, or these guys that did the calculation, okay? This is one of those crazy things that you'll never forget. This is an extremely important theoretical development. These people said there must be a chunk quark, and they told you that how big it has to be. But the pattern I'm showing you here, which appears in neutrino oscillations in any physical processes, when the fermion masses are 0 or even less pronounced, they generate. This is sufficient that the mixings disappear. Because there is no sense to talk of the mixings for such a matrix, which is invariant to any rotation in the world. That means that rotation can have no physical meaning. Whenever the rotation can be rotated away, then that rotation doesn't exist. But you don't have to trust that. And I advise you, at least in some number of processes, to see nicely how the cancellation takes place. Here it's trivial to see. If they have the same mass, they contribute equally with the opposite sign and then cancel against each other. Okay. This is the celebrated G mechanism. And you know, the G mechanism, in order to appreciate that, you should realize it has a combination of formalism and phonology. In other words, it's not that it works for any mass of the chunk quark. It is used to predict the mass of the chunk quark. So it's not that there is this deep symmetry argument of 2 generations that automatically takes care of the K long, K short. No. If chunk quark had been heavy, the standard model wouldn't have worked. Okay. Very often you will go for seminars and hear people saying that the parameter space of a theory should be something they like, something, okay? Or the theory should work for any values of the parameters. That is crazy. A good theory leaves dangerous. It works with that particular parameter that is chosen by God. And next time we'll have to talk about, we'll still go on with fermion masses and mixing. And generations, then we'll come to even more exciting issue, neutrino mass, which touches into the origin and nature of particle masses even more deeply. You will have to understand everything on a deeper level. And we will also pave the way for physics beyond the standard model. But at least I would say one more lecture about charged fermions. Any questions here? Time to stop. Rahman.
First, so these kind of oscillations will come.
Oscillations? No, I didn't. This is not an oscillation. This is not. No, I'm tempted to speak a little bit about K long, K short oscillations, K bar oscillations, but okay, sorry.
That's why I kind of coded in my mind.
Right, they are actually okay.
So they are suppressed when we go to high energies because of that reason. Oh,
I cannot go to high energies here. I was looking here, remember, at the static Hamiltonian. This I compute for vanishing external momenta. Really, I wanted to interpret this as the off-diagonal mass term for k bar. Remember, this will take k into k bar. Notice here, particle, antiparticle. They are going in the opposite directions, the quark. So if this is k, this will be k bar, and vice versa. So here, this is zero energy, if you wish. If I wanted to look at this scattering at high energies, I don't know what I would conclude, but I would.
So like it would mean that scattering of two quarks, which is not
Yeah, I don't have a physical relevance to offer you at this point regarding this analog process at high energy. But this is crucial that this was energy equal to zero. Okay, this was effective. I forgot to mention it today, but we talked about it last time. This was a static. In other words, all the external momenta are zero. Static Hamiltonian, which we wanted to interpret as a mass term. Remember, in order to transform this to the number, there is a psi bar psi thing that I sandwich into k bar, and there is not, you and I cannot know that. I just use dimensional argument there, which worked reasonably. And the reason is that it works reasonably is that it agrees beautifully with the Chang quark mass. And people have done lattice calculations to before some physical arguments to improve on that strong interaction physics. Okay, for you and me, it's not an issue here. Okay, it may reappear when I talk about QCD somewhat, but today I just need to talk about the external needed coefficient. That's it. We can turn off the machine.